Hi everyone. I'd like to take a second out to talk about when a function is or is not differentiable. So remember, differentiable means you can take the derivative, and the derivative is supposed to tell you the slope of the tangent line. So basically, when we talk about differentiability, is it differentiable? We're talking about whether or not we could draw a reasonable tangent line at a given point. So as just kind of a mini preview, I'd like you to check out this graph. We use this one for continuity as well. It has all sorts of weird features. And I want you to think about at each of the integer x values where different things are happening. So -3, -2, -1, 0, 1, 2, 3. Do you think you could draw a definite tangent line whose slope matches what the curve is doing at that point? So if you want to pause and think about that, I'll walk through it as well so you can make sure that you caught when there are problems. Okay, so if we walk through at x equals -3, we're talking about this point right here. So again, the question is, could you draw in a tangent line at that point that reasonably tells you what the function is doing? And kind of a different version of that question is basically, do you have local linearity? Remember when we first started talking about slopes of tangents, we said if you have a nice smooth function, then when you zoom in far enough, it will look like a straight line. And the tangent line is going to be the line that matches up with that linear appearance that we're getting. So at this point right here, no matter how far I zoom in, I'm always going to see this corner. So I will never be able to say this looks like a straight line, and I'm going to try and figure out which straight line that is. If you just look at this and think about drawing tangent lines, horizontal definitely just touches, but it doesn't really match the behavior on either side. Some people are also tempted just to pick one side, and you could talk about a one-sided derivative, I suppose, but we're not doing that. So you could draw a line that matches the behavior on the left or on the right, but that's actually really symptomatic of the derivative is a limit, and if the limit, if you're getting different things on either side of your x value, the limit doesn't exist. So the function is not differentiable at any sort of sharp corner, so this is out. At x equals 2, we have kind of the same trouble. We have a discontinuity. It's a little different, though. It's not a corner, it's a jump. But once again, we have different behavior on either side. So that automatically makes this not differentiable at x equals -2. And I guess you could also say, where would I put the tangent line? And I suppose I'd favor this point, but still, it's kind of a weird. If you look at only one side, it would work, but the two sides are different, so that's not differentiable. -1 is kind of the same thing. Again, these are just little variations on each other, right? So this time I actually do have the same behavior on either side, but the point is way up here. So in terms of drawing a tangent line, the point would be -1, 1, and then if I figured out slope from this behavior, I get this funny tangent line here that's not approximating the behavior of the curve. So -1, also a no-go. We got lots of problems finding tangent lines here. 0 looks great. 0, absolutely. The function is differentiable at 0. We have a tangent line with the slope of 0, so I could even say that f prime of 0 is 0. 1, it's a little more subtle, but it's still a corner. We have different slopes on the two sides, so that would be not differentiable. 2, it looks great as we come in from the left, but then this is infinite oscillation, so the question would be, where do I try and match up a slope of a tangent line? So that's another no good. And then at 3, we don't have a point period, so we can't have a tangent line. Can't have a tangent line if there's no point there. So the only integer x value of this function that we're seeing that works is 0. This function is not differentiable at -3, -2, -1, 1, 2, or 3. It's only differentiable at 0. So I just want to summarize the things that give us problems. So we will say f is not differentiable at x equals a if, okay, so first thing, if there's any sort of discontinuity, if there's a jump, if there's a point removed from the rest of the graph, if there's a hole with no point, the function will not be differentiable. So if f is discontinuous at x equals a. Okay, so if there's a discontinuity, it's automatically not differentiable. If there's a sharp corner, so if there's a sharp corner at x equals a in our picture, that was like this one right here, or this one right here, then it will not be differentiable. And then, let's see, I think I have two more. Yeah, I do. Okay, so if f, how do I want to say this, oscillates infinitely, and then the last one we actually didn't see in this picture, if f has a vertical tangent at x equals a. And a really good example of that would be like a cube root. Let's see if I can draw a cube root right. It goes like this. Right here at the origin, the tangent line would actually be exactly vertical, and the reason that's undefined is not because there is no tangent line, but because a vertical line has undefined slope. So that's why that one gives us not differential. The derivative is undefined. So not differentiable means the derivative is undefined. Okay, so that's our list. Those things would all cause the function to not be differentiable, to not have a tangent line. Thanks for watching.